Before we head back to routing, we're going to take a look at OSI layer 4, the transport layer, and what TCP and UDP are doing there. And this is the last theory-only section of the course. We're going to right back to labs as soon as we head back to routing. But this is very important stuff. I expect TCP and UDP questions to be all over your exam because we know when we have two things or three things in networking that pretty much do the same thing, but they do them in wildly different styles as TCP and UDP do, then we know that's fertile ground for exam questions. So let's start digging in here to what TCP does differently than UDP. First off, of course, we're talking about segments. We're at the transport layer. TCP guarantees delivery of segments. Sounds good to me. You know, hey, let's just go with TCP. But we have other features with TCP that we don't get with UDP. TCP performs error detection and recovery. We have something called windowing, and if you don't know what that is, I'm going to take care of that in a minute, but take my word for it right now, it's really good. And then TCP is what we call connection-oriented. And what this means is there's a two-way communication between the sender and the sendee before the data is actually sent. There's an underlying agreement on a couple of values. Now with UDP, we have best effort delivery. It sounds okay, but I don't know if it's as good as guaranteed delivery. As a matter of fact, I'm pretty sure it's not. UDP also doesn't give us any error detection. UDP doesn't give us any windowing. It's nothing personal, as you'll see with the headers. UDP literally cannot deliver these things. And then UDP is what we call connectionless, which means there's no communication before the segments start flying. They just start flying. So you look at these two things and they do the same thing, but TCP sounds a lot better because especially that first bullet point. You know, we don't get many guarantees in networking. We don't get many guarantees in life. But guaranteed delivery of segments against, you know, we'll do our best. You know, why wouldn't I want guaranteed delivery of every data segment? But there has to be a reason that we use UDP, and we use UDP for a lot of things. Our networks use it every minute of every day, especially if your network uses DHCP, which it probably does. That's the protocol that dynamically assigns IP addresses. Well, UDP handles that, so it's like, okay, UDP can't be all bad. And UDP is also used to handle voice and video traffic, and we know if there's the slightest delay in there, you know, the phone starts ringing and it's just a mess. So if TCP is so fantastic, why do we use UDP at all? And on top of that, why is UDP so popular? Keep that question in mind as we look at a couple of those details here on TCP, starting with a three-way handshake. Yeah, I thought the same thing the first time I heard it. It's like, how in the world can you even have a three-way handshake? And even if you can't have one, why would you want one? Well, with TCP, remember that underlying connection we talked about? You know, it's connection-oriented. Well, the involved devices, the sender and the sendee, to use non-technical terms, they have to agree on basic parameters of the conversation before the conversation can occur. And this agreement happens during this three-way handshake. So they agree on certain rules, they agree on where certain numbers are going to begin. And with the beginning of the three-way handshake, I would definitely have this down. The initiator sends a TCP segment with the synchronization bit set, usually just called the SYN bit, S-Y-N. And the TCP sequence number, which is a major part of TCP functions, is the primary value that is synced at this point. So we got a host and a server, host A, server A. I didn't even put any IP addresses because we don't really need them here. But here's the first shake of the three-way handshake. So even though we have a three-way handshake, we have two devices involved. So we have the SYN that goes out first. The second part of that shake is when the server responds here to the host, and it's called a SYN ACK because the server is synchronizing and also acknowledging that it received that first SYN in the first place. I know it's hard not to laugh when you say that, but that's it. That's a SYN and then a SYN ACK. And then finally, the third part of that handshake is, if you will, an acknowledgement of the acknowledgement or an ACK of the ACK. But when host A responds, then it's just an ACK. So it's SYN and then SYN ACK and then ACK. And then that's your three-way handshake. And once that's done, the segments can begin flying. Now about this error detection and recovery, you will see some books say this is not true error detection. I really don't know why. Cisco says this is error detection. It's their exam, so we're going with it. But what happens here is that the TCP header As you'll see in a few minutes, I'll show you the header. It's a lot of fields, so I want to stay here for right now. But it's got two fields, one for the sequence number and one for the acknowledgement number, two separate numbers. And it's these two values that allow TCP to detect lost segments and in turn recover from that loss. And what I'll show you in a moment is our host is sending four 2,000 byte segments after the three-way handshake is complete. And the sequence numbers are actually used by the recipient to determine the order of the segments and to anticipate the number on the next segment. And I will say right up front, your TCP sequence numbers are not going to be this neat. They can have 7, 8, 9 numbers, but for our theory, I want us to stick with something a little bit friendlier. So your host could send 4 segments over to the server, and it's got 4 sequence numbers, 2,000, 4,000, 6,000, 8,000. We can certainly figure out what the next one's going to be. And then the recipient is going to acknowledge the receipt of these segments. It sends an ACK back, just like the ACK we saw earlier, and that ACK serves 2 purposes. Now, the obvious one is that the ACK lets the sender know the recipient received the segments, because after all, it is an acknowledgement. That's what it's for. Now, the not so obvious reason is that the ACK number in the acknowledgement that's sent back, it allows the sender to determine if any segments were lost during transmission. And if they were, the sender will resend them. So it's actually the transmitting device that looks at that ACK number and says, okay, wait a minute, I think we got a little bit of a problem here. Now, the ACK is not set to the number of the last segment received. And you would think that it might be, if you hand me 4 segments and I say, hey, the last one I got is segment 8,000. What it does instead is it sets that number to the number of the next segment the recipient expects to see. This is what we call a cumulative acknowledgement scheme. And with this pattern, as we saw, the next number would be 10,000, and this allows the sender to identify segment loss, as in this situation, where the server receives 2,000, 4,000, and 8,000, but segment 6,000 got lost along the way. So what happens in this situation, we'll pick right up here at the beginning of the next video.